All right, so we're going to talk about a particular kind of function approximator that we refer to as an averager, and the whole class of averager function approximators.
Okay.
So this is a kind of function approximator that was actually, or at least in this context, introduced by Jeff Gordon. And when he did it, there was this sort of collective head slapping that happened over the entire community of reinforcement learning researchers, because it was just so there. It was so beautiful, and nobody saw it except for him. And so it really was at that time the age of Gordon.
Oh, that's fantastic.
So moving on. So we're going to introduce this averagers concept in the context of a simple example. So imagine that what we're trying to do is represent a function over the line, right? So over this one-dimensional space. So it's going to be some kind of curve. And the parameters that we're going to get to set are the actual value of that function at some particular points. So at x1, at x2, and at x3. We can, move these up and down, these points. And what we'd like is that we define a function approximator so that once we've defined these points, the rest of them will get kind of filled in a natural way, let's say.
Mm-hmm.
And for this story to make sense, they're going to have to somehow be related to averaging.
Sure.
How can we define the value of points in between here, between x1 and x2? Say we want to get the value of some point, just plain old x, as a function of the value at x1 and the value of x2. Yeah. So what would be a natural way to do that? I don't know. You can say more than one if you can think of it.
Sure. There are lots of ways of doing it, but I guess the simplest one would be just to take a weighted average based on distance.
Yes. Which is why, these things are called averages. So what we're going to do is we're going to say, okay, the value of x, I don't know what it is, but we're always going to make sure it's, I don't know, so 0.8 times the value of x1, which is a parameter, plus 0.2 times the value at x2, which is another one of our parameters.
And that's because of the relative distance between x1 and x2.
Yeah, so it turns out it doesn't matter, but that is a very natural thing to do, to kind of do a linear interpolation. And so what that means is once you nail down where x1, x2, and x3 are, the way that it generalizes, the way that it fills in the rest of the function is like, little line segments.
Mm-hmm.
There's a bunch of other things you could do, and they're all okay as long as what we do is any point that we want to define, we define it as a convex combination of the anchor points. So the anchor points are the ones that we get to set as free parameters, and the value at any other state needs to be expressible as a convex combination of the anchor points. So this doesn't really tell us what should we do for like beyond x3 for things that are out here in the state space.
Well, that's funny. That's just what I was going to ask you. What do we do for extrapolation instead of interpolation?
Yeah, so this is very interpolative. Is that a word?
It is now.
Interpolative. It's sort of interpolation related.
Mm-hmm.
So the constraint that we've got for it to be an averager, it needs to be that the value of any point is the convex combination of a set of anchor points. So we get to define how things extrapolate, but it has to be the case that, for example, for some point, I don't know, x prime out here, its value needs to be defined in terms of these black points, in terms of these other anchor points whose values are going to get to be set. So one natural thing would be to say, okay, we're out to the right of x1. Let's just set anything out here to be the value of x3.
Sure.
So we don't really extrapolate so much as just like flatten it out on the two ends, so we don't get too kind of crazy up or down from where we were. But there's other things that we could do as well. You could also say that if you're far enough away from the points, then it's going to be the average, the just straight up average of these guys.
Mm-hmm.
And as you get closer, it's going to be more influenced by the near ones. By virtue of the fact that it's a convex combination, what does that tell us about the value out here?
Well, it has to be in between the highest and lowest value, that's for sure.
Exactly. That's right. So we're extrapolating, but we're not really extrapolating outside of the data that we've got.
Okay.
And this is going to be a really important property of these averagers to make sure that they're going to be well behaved. All right. So that makes sense so far?
Yeah.
Do I have a good definition of an averager?
I think you do.